Welcome to Statistics. My name is Dr. Twane. Our topic today is the Hostelling's T-square. Now, the Hostelling's T-square is a multivariate version of our T statistics. You know that for T is given as, we say, X bar minus mu naught all over, we have S all over root N. That's T, the T statistics, and we use this when we want to compare two variables. Now, for our Hostelling's T squared, we are comparing multivariate variable. Let's see how we get the test statistics we use for the Hostelling's T squared. So if we square our T here, we'll have T squared will be equal to X bar minus mu naught all over S all over root N, all of that square. And if that happens, it will mean that we'll have X bar minus mu naught, let's say that's square. Now divide by, so we have S square all over root N square 2. Okay? And if that happens, then this will be equal to X bar minus mu naught all square. Now we can change this. And if we change this, it will be times, this is the square of root N. And that will be N. So we will now have N all over S square. Because whatever, if you have, say, this root 10 squared will be equal to 10. If you have root 20 squared, it will be equal to 20. So the square of root N will be N. Now if that happens, then it means that we will have N multiplying this will be N into X bar minus mu naught all square times we have 1 over S square, because we have already used the N to multiply this. So here we are left with 1 over S square. Remember that this S is our variance. What we started with was standard deviation over root N. So when we square the standard deviation, we now have what? The variance. Okay, so, and 1 over any value is the inverse of that value. So what we have here will be equal to N into X bar minus mu naught squared times S square inverse. Now we know that S square is the variance, but let me use capital S to indicate the variance. So instead of writing S square, let me use, this is small s, and I'm using here capital S. So I'll just write capital S inverse. That is, instead of saying capital S raised to power minus 2, which is what we have here, 1 over S square is, will be S raised to power minus 2. But if we have S raised to power minus 1, we know that we're looking for the inverse of this. And this one, as it is, what we are considering is a matrix. So now because of this square, we can just decide to write this as N into X bar minus mu naught. Then we have S inverse again, X bar minus mu naught. Now this becomes our Hostelling's, the test statistics for our Hostelling's T square. So this is the test statistics. Now what we have here is a vector. This is also a vector, and this is a variance covariance matrix, because we are dealing with multivariate. This is a vector, this is a vector, and then this is a variance covariance matrix. Now, having said that, in most books, you see that your T square is given as N D bar transpose. Then you have your S inverse D bar. Now, what this means is, this is exactly what we have here. This N is this. Now, X bar minus mu naught. Sometimes what you are comparing could be that it has a standard. Now, if there is a standard, now when you collect your own data and then you collect, and then you compute the mean of that data. You are comparing that mean with the standard. So we want to either compare what we have got from the sample with the standard. So in that case, this mu, which is the population mean, is the standard, and then this will be the mean of the sample we have just collected. Now, there are cases also where we are comparing these values against each other, like what happened before and what is at the moment. In situations like that, you may not be comparing with the standard. You may be comparing what happened before and the present. So the value of this d is obtained from the difference between what was before and what is. And remember, like we said, this d is a vector because the mean of those multivariate variables. You understand? So that will make this a vector. This is also a vector, and this is a variance covariance matrix. Now, having laid this background, let's solve a problem. A community several kilometers away from an oil spill site claimed that her stream was impacted by the oil spill. The physiochemical properties before and after the spill are tabulated below. Using the Hostelling square test, confirm or dispute the claim of the community. So in this case, what we are expected to do is to conduct the Hostelling square to confirm what the community claimed, that the oil spill impacted their community, or we dispute their claim. Now, this is the data. These are the data on the physiochemical parameter of the stream before and after the oil spill. Now, before the oil spill, the pH of the water taken at different locations were 7.5, 7.2, 7.1, 7.0, and 7.3. But after the oil spill, the pH is 5.3, 5.8, 5.2, 4.3, and 5.5. We also have the data on total dissolved oxygen before and after. Now, for us to conduct Hostelling's square, now, one, we must write the hypothesis. And what is the hypothesis? We will say that HO, that our mu naught is equal to mu 1. Now, what are we saying? We are trying to equate the mean before and mean after. Are they the same? Remember that we are comparing multivariate variables. And now this is multivariate in the sense that for this stream, we are comparing, we are looking at both the pH of that stream and also total dissolved oxygen. And now after, we're also looking at the pH and total dissolved oxygen. And we are going to look at all of them simultaneously. Probably, we would have just decided to just compare pH and pH using T value, and then we'll continue. Or we'll compare our total dissolved oxygen and then before and after, and then using our T statistics, and then we'll conclude. But sometimes we have seen that there's always inconsistency in that, and that's why in cases like this, the Hostelling square is preferred. So this hypothesis is saying that the physiochemical parameters of the stream are the same before and after. Okay, now if we have stated the hypothesis, the next thing is to do what? Look at our test statistics. Note that our test statistics, T square, is equal to, we said, N into this bar transpose. Then we have our S inverse D bar. We'll come into to tell the explanation of all of this. We have said that this is the number of observation, and then this is a vector of the mean. This is a variance covariance matrix, and then this is also vector of the mean. But we will not forget this transpose because it's very important. Without this transpose, you have difficulties in the multiplication of the matrix. So for you to have that conformity in multiplication, This transpose is very important. Now, this is this variance covariance matrix will mean that we have to compute the variance and the covariance. And so for us to compute the variance and covariance, we need to get the vector first. And so how do we get the vector? We are going to create a column. Let's create a column and call that column. Let's create a column and call that column D1. So that D1 should be the difference between the pH. So the pH in this case is Y1 and X1. So we'll just indicate here Y1 minus X1 is our D1. Okay, so now we're also going to create another column and call it D2. So that D2 will be the difference between our total dissolved oxygen, which is Y2 and X2. So we indicate Y2 minus X2. Okay, now let's get that. What is D1? If we say 7.5 minus 5.3, that will be 2.2. 7.2 minus 5.8, 1.4. 7.1 minus 5.2, 1.9. So if we sum that, it will give us exactly 10. Okay, so our D2 will be 6.1 minus 6, 0.1. So this will be 6.0 minus 5.3, 0.7. 6.4 minus 1.9, 0.8. So if we sum this, it will give us exactly 5. So if we have 5, now note that our D bar is the mean. D bar is the mean of D. In this case, we have D1 and D2. So the mean of D1, so that we say our D1 bar will be equal to summation of D1 all over N. And our sum of D1 is 10. Our N is what? 5, number of observation. And that's going to be equal to 2. Okay? Now our D2, D bar 2 will be equal to summation of D2 all over N. Remember, in this case, we can call this N1 and call this N2, which will be sum of D2 is 5. And N is also 5, so that will be equal to 1. So it means that we can come here to say that our D bar is equal to what? 2 and 1. So that's the vector we talked about, that our D is a vector. This is the mean of the difference of the first variable, pH, and this is the mean of the difference of the second variable, total dissolved oxygen. Okay. Now, the next thing will be to look at this variance covariance matrix. So to calculate the variance, you know that for us to get the variance, it means that we're going to create a column, call it D1, small d. We are using small d because we want to look at the difference between this and the mean. Now for D1, the mean is 2. The mean, for D2, the mean is 1. So D1 is going to be what? Small d1 is going to be capital D1 minus 2. So that our small d2 will be equal to our capital D2 minus 1. Okay? Now, once we do that, you see that here, D1 is 2.2, and the mean is 2. So 2.2 minus 2, 0.2. 1.4 minus 2, minus 0.6. 1.9 minus 2, minus 0.1. If we sum this, it will be 0. And that confirms the characteristics of arithmetic mean. that deviation from mean will always be equal to 0. So that mean is correct. Now in this case, this is our D2, and the mean of D2 is 1. So 0.1 minus 1 minus 0.9. 0.7 minus 1 minus 0.3. 0.8 minus 1 minus 0.2. Also, if we sum that, it will be equal to 0. Now, because of the formula of variance, we'll create a column and call it D1 square, create another column and call it D2 square. Then, for our covariance, we are going to create a column and call it D1, D2. D1, D2. Okay? So D1 square will be, this is 0.04. The square of minus 0.6. Okay, 0.36. So this is 0.01. Now, if we sum that, it will give us 0.94. Okay? Now, our D2 square will be the square of this. So this will be 0.81. This is 0.09. This is 0.04. Thank you. So, and if we sum that, 2.42. So now, D1 for the covariance will be 0.2 times minus 0.9 minus 0.18. Okay. Now, minus 0.6 times minus 0. That will be the same, that will be 0.18. Then 0.1 minus 0.1 times minus 0.2. 0.02. And if we sum that, minus 0.08. Okay. Now, we can continue with this. Now, the variance, let me put it var D1, variance of D1. Variance of D1 will be equal to, we have summation of D1 square all over n minus 1. Summation of D1 square over n minus 1. And this will be equal to, now this is D1 square, 0.94 all over our n is 5 minus 1, which is 0.5 minus 1. Let me just put it. It's 4. So instead of saying 5 minus 1, let me just say 4. Okay? Which is 0.235. Okay? Alright. So variance of D2 will be equal to summation of D2 square all over n minus 1. And that will be equal to, the sum of D2 square is 2.42 all over 4. And that's what 0.605. Now, the next thing is the covariance. Covariance will be equal to summation of D1, D2 all over n minus 1. And that will be equal to minus 0.08 all over 4. And that's equal to minus, this is equal to minus 0.02. So this is the information we need for our variance covariance matrix. And so we'll say that our S, I'm just writing S, not S inverse. So when we have the S, we can now compute the inverse. So that our S will be equal to, now our D1, the variance of D1, 0.2 2, 3, 5. Then the covariance is minus, remember it is the covariance D1, D2, and D2, D1. So D1, D2 is minus 0.02. So D2, D1 will be minus 0.02. And then D2, the covariance, the variance of D2, the variance of D2 is 0.605. So this is our variance covariance matrix. Now, when we have this matrix, the easiest thing to do is to, first of all, in order to compute, because what we actually need is the inverse of this matrix. Because look at what we have here, S inverse. So this is a matrix. How do we get the inverse of this matrix? Now, to get the inverse of a matrix, we'll need to, first of all, get the determinant of that matrix. And the determinant, this is just 2 by 2 matrix. So this time this minus this time this is the determinant of the matrix. Then we'll need to get the minor. Now when we get the minor, we also get the cofactor. Cofactor is just minor with the appropriate sign. Then from cofactor we'll get the adjoint. And the adjoint of the matrix is the transpose of the cofactor. And just like what we are seeing here, this matrix is a symmetric matrix. You can see that off diagonal are the same. So it's symmetric. And so if you take a transpose of a symmetric matrix, it will give you the same thing. So whether we transpose or not, you see that the cofactor is the same as the adjoint. So that the determinant of this S will be equal to, we have 0.235 times 0.605 minus 0.02 times minus 0.02. Okay, so which will be equal to, if we multiply this, 0.1422 minus, if we multiply this, 0.0004, and that will be equal to 0.1418. So this is our determinant. Okay, so we are going to clean this other side. All right. Our matrix is S is equal to, we have 0.235 minus 0.02 minus 0.02 and 0.605. Now to get the minor of this matrix, let me write it this way. Minor will be equal to, now when we look at this particular value, we just roll the row and the column. So what will be left is just this value. We have 0.605. And so when we, this, like we say they are symmetric, so whatever, it will remain the same. So this is going to be, when you hold this, this goes, this is what remains, 0.02. When you hold this, this goes, this is what remains, minus 0.02. Note there's a minus here. And then when you hold this, this goes, this is what remains, 0.235. Okay? So that's a minor. Now, the cofactor will be equal to, now, this minor with the appropriate sign. And you know that what we are looking at, like we said earlier, is that we have A11, A12, A21, A22. So the sign plus, minus, minus, plus. Okay? So the first one is plus. This will be 0.605. The second one is minus. Time this minus. So it's going to make this a positive value, 0.02. This is minus. Time this minus to make it a positive value, 0.02. Okay? 0.02. and then this will be, this is plus plus 0.235. Okay, so that's the cofactor. Now the transpose of this cofactor will be the same thing because this is symmetric. But we can still write the adjunct. And we said adjunct is a transpose of this. And if we transpose this, it will be this value. That is the role becoming the column. But it's, which remains the same thing. So, but let's just write that our adjunct is equal to 0.605, 0.02, 0.02, and then 0.235. That's our adjunct. Now, in the cofactor, we are saying that the transpose of the cofactor is the adjunct. And how do you transpose? We interchange the role with the column. What's the first role? This is the first role. 0.605 and 0.02. We'll make that the column. And so it's 0.05, 0.02. This rule is now the column. The second rule will now be the second column. So we have 0.02 and 0.235. Ahead. So that's the adjunct. So now our inverse will say F inverse will be equal to, we have 1 over the determinant times the adjunct. That's the formula for inverse. So which will be equal to 1 over, we got our determinant as, we have 0.1418. Then into, what is our adjunct now? 0.605, 0.02. Now, 0.02, 0.235. Okay? So if we multiply this, it will give us, it's just like dividing each of these value by 0.1418. But when you multiply this by this, multiply it by this, so that will give us, we'll say our S inverse is equal to, if we divide this by 0.1418, what will it give us? 4.266. Okay? Then when we divide it by 0.02, 1410. So this will also be 0.1410. And then this will be, if we divide 0.235 by 1.6570. 73. Okay. Okay, so that becomes our inverse. Okay. So if we have that as the inverse of our matrix, then what we have to do is now to look at our test statistics. We said t square is equal to n into n d var transpose and S inverse d var. Okay? So if we have that, then it will be equal to, our n is 5, d bar is what? Look at our d bar here. 2 and 1. But the transpose, you know, this is a vector and a column vector. The transpose of this column vector will be what? A row vector. So instead of having a column vector, we now have row vector, which will be 2 and 1. Okay? Then our S inverse is the whole of this. We have 4.2666. This is a 0.1410. And then we have 0.1410 and 1.6573. Okay, and after that we also have D bar. So that D bar we know is 2 and 1. That remains a column vector. Yes, since it's not a transpose. So this is easier for us to multiply. So this will be equal to, this time this is 10, this time this is 5. So this is our row vector. So we have 4.2666, 0.1410, 0.1410, and 1.6573. So we have multiplied this one. Now this one now, 10 times 4.266. Was so it 42.666. Then 5 times 0.705. Okay? Like this time this and this time this. Now the next one is going to be 10 times this, 1.410. Okay? Then 5 times 8.2865. Yes, it's correct. So this, and then we have 2 and 1. Okay? So if you add this and this, 43, 43.371. And if you add this and this, 9.6965. So that is what we are multiplying by 2 and 1. Okay? Now look at the nature of the multiplication now. This will multiply this plus this times this. So this times 2 will be equal to 86.742. Okay? Plus this times 1 will be the same thing. 9.6965. And that will be equal to, so that our t square is equal to 96.4385. So this is our test statistics, 93.4385. Now note that we can compare this value with the tabulated value. There is a table for t square, but because it's not as common as that of f. Now f is used in most of the software, so I prefer we use our f to compare. Let me clean this. So now f is given as n minus p all over p into n minus 1 then times t squared. So that's going to give us it's just like a conversion, so to speak. So now this will be equal to, we said our n is 5, is it not? So we have 5 minus p is the number of parameters. So we have two parameters here. One is the pH, the second is the total dissolved oxygen, which is 2 all over. Our p again is 2 into our n is 5 minus 1. Then we computed our t as 96.4385. So this will be equal to 5 minus 2 will be 3 all over. 5 minus 1 is 4 times 2, 8. So we have 8 into, we have 96.9385. So 3 times this value 89.3155. All of that over 8. That will be equal to 36.1644. So our F is 36 points. Now, the critical F will be obtained from, we have F, alpha, P, and then N minus P. Okay, that's how to get our critical F. So which will be equal to, we have F, the alpha is 0.05, P is a parameter, which is 2, N minus P, which is 3. So if we look at F table, 0.05, 2 under 3, the value is equal to what? 5.779. So what are we doing? We are comparing the computed value, which is, call it our F car, which is equal to 36.1644, and that value is greater than the F critical, which is equal to 5.79. Therefore, we reject the norm. And remember, the norm was saying, look at what we had. We said HO said what? Mu naught is equal to mu 1. That mu naught is equal to, which means that the mean before is equal to the mean after. So if we are rejecting that, it means that we are concluding that, yes, it's not the same as the mean before. So which means there would have been an impact as claimed by the community. Because what was is not the same with what is. So the physiochemical parameters before and physiochemical parameters after are not the same. Particularly, the pH and dissolved oxygen before are not the same as the level of pH and dissolved oxygen after. Thank you very much. I hope you understand. If you have any question, feel free to go to the comment section. Do well to like our video. Please, if you have not subscribed to the channel, just click on that subscription button. It's free. Thank you and God bless you.